In this presentation, I'm going to give you a bigger picture of 5G, and then I will dive into details of some of the important aspects of 5G. I'll first give an overview of 5G, then I'll get into the details of some of the key aspects, including the numerologies, protocol stack, initial access, control channels, data channels, beam management, and bandwidth part. This presentation is based on 3GPP release 15, which is the first release of 5G standards. And I also would like to thank my colleagues in ESG for providing the content. 5G is intended to be scalable in terms of services and devices. There are three major services: enhanced mobile broadband, mission-critical control, and massive Internet of Things. For enhanced mobile broadband, it's featured with a very high data rate, more than 100 megabits per second per user. For mission-critical control, it's featured with very high reliability and a very low latency. And for massive IoT, it features very low power operation and very high device density. Let's look at the 5G NR specifications timeline. Release 15 was finalized in June 2018. It supported both non-standard mode or NSA and the standard mode or SA. More features were added to Release 16 to better support services such as URLLC. Currently, we're in the work item phase of Release 17, which has expanded the scope of 5G NR by including new platforms such as the satellite, which is called a non-terrestrial network in 3GPP. Also, 3GPP will continue to evolve LTE in parallel to better support massive IoT services. Here are some of the key air interface enablers. The first one is a scalable OFDM waveform. Like 4G, 5G continues to use OFDM as the waveform. However, the 5G waveform supports multiple subcarrier spacings, can address diverse spectrum and deployment scenarios. The second one is flexible slot-based numerology. With this, 5G can support very low latency operation, and it is also forward compatible. The third one is the use of a millimeter wave spectrum. This greatly increases the amount of bandwidth for the system, can enhance the system capacity and throughput. The next enabler is massive MIMO. By leveraging a large number of antennas, the 5G can increase the capacity significantly. 5G also uses a beam-based operation. This is especially important for millimeter wave because of the large path loss. By using many narrow and high-gain beams, 5G can close the link even for a very high frequency in the millimeter wave. Finally, 5G uses advanced channel coding schemes, including LDPC for the data channel and polar code for the control channel. And LDPC can provide very high throughput that meets the demand of throughput for 5G services, and the use of polar code can provide very reliable control channel operation. 5G now supports multiple subcarrier spacings. Besides the 15 kHz that is supported in LTE, there are also the 30 and 60 kHz for sub-6 GHz. For millimeter wave, the minimum is 60 kHz and the maximum is 240 kHz. Higher subcarrier spacing is beneficial to provide robustness against frequency offset and also things like phase noise. 5G now supports a wider range of channel bandwidth. Release 15 supports a maximum of 275 PRBs. Each PRB consists of 12 subcarriers, with a larger subcarrier spacing compared to LTE. 5G can support a maximum of 400 MHz channel bandwidth. 5G now also introduces the self-contained slot. The motivation is to reduce latency. For instance, the downlink data and the uplink acknowledgement ACK or negative acknowledgement or NAC can be sent in the same slot. This can significantly reduce the latency. Also, the downlink grant and the uplink data transmission can occur in the same slot. 5G has two modes, the standalone mode or SA and the non-standalone mode or NSA. In the standalone mode, the control plane and the user plane are provided by 5G. In the non-standalone mode, the control plane is provided by 4G and the user plane is provided by 5G. As shown in this diagram, the blue portion is for the standalone mode and the green portion is for the non-standalone mode. The motivation of having the non-standalone mode is to leverage the existence of a 4G core network to speed up the deployment of 5G. The 5G protocol stack is the same as the 4G protocol stack, except that 5G has an additional sublayer, SDAP, which stands for Service Data Adaptation Protocol. In 4G, the service is provided by the EPS bearer and the radio bearer. In 5G, the EPS bearer is placed by the PTO session, which consists of one or multiple quality of service flows. When the network configures the radio bearer, it will indicate, for the case of NSA, whether the radio bearer is associated with the 4G core network or the 5G core network. This diagram shows the location of the SDAP in the protocol stack. It is between the IP layer and the PDCP layer. Now let's take a closer look at SDAP. The traffic in the downlink entering the base station is in the form of quality of service flows or QoS flows. SDAP maps QoS flows to data radio bearers or DRBs. In the uplink, SDAP performs the reverse process, meaning that mapping DRBs back to QoS flows. Additionally, SDAP performs reflective quality of service. It derives the quality of service rule for the downlink and applies that for the uplink traffic. This can save on the control signaling for configuring the quality of service provisioning for the uplink traffic. Now let's look at initial access, including cell search and random access. Initial access is based on detecting and processing the SSBs. Like LTE, NR also uses primary synchronization signal, secondary synchronization signal, SSS, and PBCH, physical broadcast channel, to send critical system information to enable initial access. In NR, these three, PSS, SSS, and PBCH, have a particular structure in the time frequency resource grid. The structure is shown in the diagram. The SSB occupies 4 OFDM symbols. The PSS has 127 subcarriers, and the widest bandwidth of the SSB occupies 20 RBs. There are some blank subcarriers next to the PSS and SS. The purpose is to facilitate synchronization. Multiple SSBs can be further organized into SSB burst set, and these burst sets can appear periodically. Each SSB in SSB burst set has SSB block index. The SSB periodicity is configurable. For initial access, it is 20 milliseconds. This diagram shows an example of SSB burst sets and the periodicity. Each burst set consists of 4 SSBs indexed by 0, 1, 2, 3. Each SSB in the burst set may be transmitted in a different spatial direction. Each SSB carries a PBCH, which is self-decodable. The payload of a PBCH includes a master information block, or MIB for short, plus some additional bits. The master information block, or MIB, remains the same among 4 repeated SSB transmissions in a span of 80 milliseconds. A UE can combine these repeated transmissions to do soft decoding, which can improve the performance. This is similar to the design in LTE. ENA supports beamforming, which can be used for SSB transmission. Because of beamforming, an SSB transmission only covers a small portion of the space. To make sure every UE in the cell can receive the SSB transmission, the base station can form multiple SSB transmissions pointing to different directions in space. This is the beam sweeping concept as shown in this diagram. A UE determines the random access resource based on the SSB index. The association between the SSB index and the random access resource also let the base station know which SSB works best for the UE. A random access resource is also called a right location. The diagram below gives an example about the association between the SSB index and the right location. The UE monitors all 4 SSB transmissions. Suppose SSB2 has the highest quality. The UE can transmit a PRH preamble in the right location corresponding to SSB2. In this example is RO2. By receiving a PRH preamble from that UE in RO2, the base station knows that SSB2 is the best SSB for that particular UE, and it can use that information for future beamforming to that UE. Now let's look at the control channel. The control channel ENA is different from the control channel LTE. ENA uses the concept of a CORESET. A CORESET is a set of resources in the time and frequency resource grid. However, the starting OFDM symbol location is not determined, so that a CORESET is a block of resource floating in time. The duration of a CORESET is up to 3 OFDM symbols, and the frequency resources are a multiple of 6 PRBs. The CORESET configuration and the search space configuration together determine the possible candidates for the resources for a PDCCH. A UE decodes a PDCCH by blind decoding. There's a special CORESET, which is referred to as CORESET 0. CORESET 0 carries a PDCCH, which schedules a PDSSH, which in turn carries System Information Block 1 or SIP1. SIP1 is also referred to as Remaining Minimum System Information or RAMSI. RAMSI includes cell selection information, the configuration for initial bandwidth, the parsit, etc. A UE first decodes SSB, and then by using the MIB information that indicates the relative location of the CORESET 0 to the SSB, the UE can go to decode the PDCCH, and then continue to decode PDSSH by using the information in the PDCCH. There are several time and frequency multiplexing patterns between the SSB and the CORESET 0. They are shown in the diagrams. Now let's look at the data channel processing, which applies to both the downlink and the uplink. Let's start with the transport block. We first calculate the CRC and attach the CRC to the transport block. In NR, the channel code for the data channels is the LDPC code. There are two base graphs defined. Roughly speaking, for lower coding rate and shorter transport block size, base graph 2 is selected, otherwise base graph 1 is selected. To limit the complexity of channel coding, the transport block with the CRC is segmented into code blocks, which are then individually encoded by LDPC. The outputs are rematched to accommodate the available resources. And then the resulting code blocks are concatenated and scrambled. The purpose of scrambling is to reduce the interference, randomized interference. And then modulation will be done, and the symbols are mapped to different layers, and precoding is done, and the outputs are assigned to different antenna ports, and there will be additional optional step of frequency interleaving by using this VRB to PRB mapping, and then the OFDM signals will be generated and transmitted. In 5G NR, for high frequency, the path loss is large. To compensate for the large path loss, we can use a large number of antennas to form very narrow high-gain beams. However, since each beam is very narrow, it only covers a small portion of a cell. The solution to this issue is to use beam sweeping. By beam sweeping, the coverage can be significantly extended. For the downlink MIMO, NR supports only non-codebook based transmission. Basically, the data and the reference signal, which is the DMRS, are transmitted with the same precoding matrix. This reference signal will help the UE to estimate the joint channel that comes from the precoding matrix and the actual physical channel. As a result, the UE doesn't need to know the precoding matrix in order to process the received data. In the uplink, NR supports both codebook-based transmission and non-codebook-based transmission. Let's take a look at the example in the diagram. For codebook-based transmission, basically, the UE transmits a reference signal, and the base station estimates the channel and signals the precoding matrix back to the UE for the uplink transmission. In this diagram, the UE uses two reference signal resources, or SRS resources. Each one is used for an antenna panel, and within each antenna panel there may be multiple antenna ports. So a sequence is assigned to each port, and they are cyclically shifted to maintain orthogonality among themselves. The base station then estimates the channels for both antenna panels and then feeds back SRI, which indicates which SRS resource is selected. And this also conveys which antenna panel should be used for future transmission. Also, the base station signals the precoding matrix, also the rank associated with the selected antenna panel. And then the UE will transmit. Now let's look at the other case, the non-codebook-based transmission in the uplink. Again, let's take a look at an example. Here, first, the base station will transmit some reference signal in the downlink, and the UE uses the reference signal to estimate the downlink channel. This is based on the assumption of channel reciprocity, which is valid for TDD. Then, the UE will transmit SRS in the uplink, the precoded SRS in the uplink, and the base station will feed back an indicator of the SRS, which selects a subset of the precoding weights, and then after that, the UE will transmit data using the selected weights for the uplink precoding. Beamforming is important technique for 5G NR. So let's look at the beam switching procedure. This diagram shows how the base station changes its transmit beam. And this is based on the measurement report from the UE for different beams. And the base station can make a decision to switch the beam based on the measurement, which is the layer 1 RSRP measurement. Now let's look at how the UE can refine its receive beam. So this is done by letting the base station transmit a reference signal, which is a CSRS, in a repeated manner so that the UE can try different receive beams to see which one works best. Now let's take a look at the bandwidth part, or BWP, which doesn't exist in LTE. The bandwidth part is a set of contiguous PRBs within one carrier, and it has its own subcarrier spacing. Also, it has associated properties, configurations on the control channel and data channel. The motivation of using bandwidth part is to enable flexible operation of different types of UEs. For instance, the base station may operate in a very wide bandwidth, but there may be different types of UEs, and because of a power consumption limitation, some of the UEs can only operate in very narrow bandwidth. So using bandwidth part, we can enable different UEs using different bandwidth parts communicating with the same base station. This diagram shows a few examples of bandwidth parts. Here, each bandwidth part has its own cyclic prefix, and the location and bandwidth in the time and frequency resource grid. Also, different bandwidth parts may have different subcarrier spacing. A bandwidth part may have its own CORESET. There are different types of bandwidth parts. For instance, there's the initial bandwidth part. That is the bandwidth part where the UE will do random access. And there's also the default bandwidth part, which is the one for the UE to fall back on when the UE is inactive on the different bandwidth part for some time. And also, the system can configure a first active bandwidth part, which is the bandwidth part to be used after the UE is configured with additional bandwidth parts in addition to the initial bandwidth part. In this diagram, we see that the initial access and random access both occur on the initial bandwidth part, and after that, the UE can, by configuration from the network, operate in a different bandwidth part.